Okay, good afternoon, 61C. Good afternoon. Great. Wonderful day to be alive in California. Okay, so today we're going to talk about the whole process of compiling, assembling, linking, and loading everything from writing your text code to getting the thing running on a real machine. So we're going to go all the way through this software tool chain that's between your C code and the actual hardware. So when you want to run a program on a machine, there's a lot of different ways of doing it. And there's this continuum from what we call interpreting the program to compiling it down. If you look at the ways in which you represent a program, you can represent it as the original source code, and that can be done in different levels of language. So something like Scheme or Python are very high-level languages, very high-level way of representing a program. Somewhat lower-level languages, things like Java, or even lower-level, C++ and C. But if you go all the way down, there's even lower-level languages that we've already seen, like assembly code, a very low-level way of representing a program. Now, along this spectrum, as you go from very high-level languages to very low-level languages, the high-level languages are very easy to program in because they're taking care of most of the details for you, whereas the low-level languages, you have to take care of all the details as a programmer. On the other hand, if you think about how easy it is to interpret the program, to have some program execute your program, the high-level languages, every statement encodes a lot of work, and so it's a lot harder to actually execute that program. Whereas if you go all the way down to machine code, the programmer's done all the work for you. It's very efficient to interpret that low-level code. So if you think about interpreting versus compilation, an interpreter directly executes the program in its own source language. So the interpreter looks at the code and runs through the code, and as it looks through the code, it's doing the actions the code specifies. And if you jump back to a piece of code you've seen before, you do that interpretation over and over again. Right? So interpreter is continually looking at the source language and figuring out what to do next. Translation is a more efficient technique where you look at the program once and translate it down to low-level form in one go, and then you can run it at the machine level. So an example of interpretation is Python, that hopefully all of you remember seeing. You write your program in Python, it's just a script, you then just run it. And it just runs. There's no compiler, there's no linking, there's no loading as far as you're concerned. You just take that script and just run it straight away. Well, what's happening under the hood is that Python script isn't actually running directly on the hardware. Your Python script is just data to a program, which is the Python interpreter. So that program is compiled and runs on the hardware, but that program in turn looks at your source file in Python and figures out what the program needs to do. As a result, because you don't have all these compilation steps, it's very quick to write a script and get it running. But because you haven't done that translation, this interpreter has to do all that work every time it sees a piece of code, and so as a result, the code is very slow, maybe 10 to 100 times slower than if you compiled it, right? Because you're redoing this work every time you see the same piece of source code, okay? So interpretation is seems very quick. It's very quick to get your programs running, but it's usually a very slow way of running a program. Now, we don't just interpret high-level programs like Python code. It turns out that sometimes it's useful to interpret even very low-level programs, even machine code. One example you'll see in the class is Mars, which is a MIPS simulator. So it takes MIPS code and simulates it on a machine. One reason we do that is because the machines you use in the lab are not MIPS processors. They're Intel x86 processors, a different instruction set. And so we write an interpreter that understands the meaning of the MIPS binary code and just runs it on top of a different instruction set. So it's just interpreting it. So that's one reason why you might interpret a very low-level language. Another interesting case study is when a company changes instruction sets. So when the Apple Mac first came out, it was based on the Motorola 68000 ISA. And this was one of the early 32-bit, 16/32-bit processors. It sort of came out at the end of 79, 1980 timeframe. It's a very popular microprocessor. The Macintosh was based on that. The Macintosh came out in 1984. It was based on the 68000. So the classic Mac was based on this ISA. All the code was written for this ISA. Over time, processors built for that ISA were not very competitive, and there was a new movement, the RISC movement, you'll hear a bit more about later, And IBM was developing a processor called Power, which was a RISC-style processor. And Apple decided to move Macintosh to the Power architecture. And they actually formed an alliance with Motorola, who were doing the 68000, IBM, who were doing the Power architecture, and Apple. And they formed a new consortium to develop something called the Power PC, which was the Power architecture designed for PC-class machines, like the Apple Mac. And so then Apple moved all their code, all their machines stopped being 68000 processors with 68000 instruction sets to being Power PCs with Power PC instruction set. And what that meant was all the programs that were compiled for the 68000 couldn't run natively anymore. The instructions didn't make any sense, so there's different instruction set. So what they actually did was, instead of saying all that code you have doesn't work on these new Macs, that would be commercial disaster for a company, right? To say all the software you bought, the next Mac doesn't run the software your old Mac does. Instead, what they did is they shipped with the Power PC machines an interpreter inside the machine that would, in software, interpret the 68000 code and pretend it was a 68000 processor, even though it was a Power PC. Now, this wasn't as fast as if they actually had built it in hardware, the 68000 machine, but it was pretty fast because the new processors were a lot faster than the old ones, right? So they could get away with this emulation overhead to some level. Now, curiously, Apple is a very nimble company, so after a while, IBM was just not really interested in the small machine space, building processors for small laptops. And so Apple looked around and they saw, well, Intel's been shipping these chips, doing pretty well, and they have very aggressive plans for low-power portable chips. And so Apple decided to switch from PowerPC to Intel's x86 architecture. Okay, so this is a second complete change in the instruction set in the Mac line, right? They've gone from 68000 to PowerPC, and now they're going from PowerPC to x86. This time around, they had the same issue, though, that there's all this software that was written for PowerPC now, and now I have to move it to x86. Question?
So oftentimes when you're downloading software, it even has like Mac PowerPC or Mac x86. So wouldn't you theoretically be able to just have the same code and have it compiled into different instruction sets, rather than to two separate files, I guess?
Right, exactly. So that's a good point. So you'll see that some programs, you have a PowerPC version and an x86 version, and those are the two different. They'd be compiled for those two different ISAs. You just download the one your machine has. So that works if whoever wrote the software is prepared to compile it twice and make available those two versions. However, a lot of companies had written stuff that they weren't going to recompile for x86, or you had some software from a company that went out of business, right? And this is something you rely on, and it's not supported anymore. And you just have the PowerPC binary. So what are you going to do? And what happened was Apple shipped a form of interpreter, but a more efficient one, a dynamic translator called Rosetta. And this would, on the fly, look at the PowerPC code and translate it into x86 code. And remember how it done the translation, so you weren't quite doing it over and over again. So it was reasonably fast performance for the old PowerPC code. And this was a necessary technology for them to make the switch, because otherwise they would have left a lot of their customers behind. And the problem is, if you just say, I'm going to do something completely different, at that point your customers say, well, should I move to the new Mac, or should I move to Company X? I have to throw away all my software anyway, so why don't I shift completely to somebody else? So they're really incentivized to keep all your old software running as they change instruction sets. Now, changing instruction sets is a big cost to a company for all these reasons, and so you don't do it. It's a very big deal when they do this. And even a few months before the change happened, there were a lot of people saying there's no possible way that Apple will shift away. Absolutely no chance they'll move from PowerPC. It'll be too costly. But lo and behold, they had this stuff running in the labs for years before, because they're a smart, big company, and they'll be running all their OSs on lots of different ISAs internally to make sure they can make the change. So, for example, right now, another big controversy is whether Apple is going to stop using x86 in their laptops and move instead to the ARM instruction set, which is used in the iPhone and the iPad. I don't doubt that they have all these systems up and running on ARM processors internally. I'd be upset as a shareholder if they weren't doing that, right? It's a very sensible thing for a company to be doing, so they probably have that. Whether they'll make the switch depends on business reasons, but you can be assured that they have complete prototypes of this stuff running on the ARM instruction set internally in case they want to make that change, right? So you may even want to do interpretation of machine language. And remember, this is one of the great ideas in architecture, these layers of representation and abstraction. If you precisely define the interface, what the semantics are, you can replace the implementation with many different implementations that all look the same to the next level up. Okay, another thing about interpreters, they're very easy to write. In fact, we used to have one of the projects in the class would be an interpreter for MIPS. You would write in C. We changed it around to give you a different project this time. But usually they're a lot slower than doing direct translation. Okay. So when you do this translation, you almost always get much more efficient performance. And all high-performance applications and operating systems, for example, are written in, are compiled down. Another advantage, if you're a commercial entity, is when you compile the code, you ship the binary. It's pretty hard to reverse engineer what the source code was. So it's a way of hiding your source code, if you like, instead of shipping. If you had to ship the source code to everybody to run on their interpreter, everybody could see all your code, right? So that's another advantage to compiling. So the main one is really the efficiency. All right, let's take a look. What we're going to do now is sort of go through all the steps that happen in compiling a C program and actually having it loaded and run in a system. Okay, so starting at the top, you have the text file, foo.c. We go through a compiler, we get an assembly program out. We then go through the assembler, which takes the assembly program and produces an object file, which is a low-level machine code representation of that one source file turned into machine code. Then we go through a linker, which takes all these pieces, different object files, combines them all to give you a single big program, an executable. And then this executable is then loaded into the machine and you start running. So you load that executable into memory and start running it. So those are all the steps you have to do when you compile a program. Now contrast this with the diagram for interpreting, where you just had the source code in a file and you just ran the interpreter. That was it, right? So compilation has all these steps along the way to get you a running program. So we're going to go through these. So one by one, at each level, what I want to talk about is what's the input, what's the output, and kind of what happens along the way for each of these phases. So a compiler is the first step, where we take the high-level code, so foo.c, piece of C code, and the output is going to be assembly language for the MIPS processor. So at this stage, the compiler is specializing it for given instruction set and outputting assembly, but the assembly is still not the ones and zeros. This is still a little bit higher level than the actual ones and zeros, right? It's just assembly code. And in particular, in MIPS assembly, the assembly code may contain what we call pseudo instructions, which are really just shorthand for other instructions or short sequences of instructions, right? So one example here is, there's a move pseudo instruction. This isn't a different instruction in the instruction set. All it is using the add instruction to add 0 to register and put the result in the destination. So it effectively copies the register by adding nothing to a value and moving it over. But instead of writing this in your code, you just write move. It's a lot clearer what the intent was, as well as fewer characters in the text file. All right. So these pseudo instructions have to get expanded out to the actual literal machine instructions. But that happens in the assembler. So we're talking about the compiler. So the compiler takes C code and produces assembly code, and the assembly code will have pseudo instructions in there. Right. The compiler doesn't care about expanding them yet. Okay. So this whole process of compiling C programs into assembly code, and it's basically compiler technology. For the last few decades, people have figured out really clever ways of doing this and generating efficient code. If you want to learn more about how to write a compiler, you should take CS164 as the operative class in which you learn all about how to write compilers. So in this class, we're just going to assume somebody else has done that brilliant work, and we're going to look at the assembly language and go on down. You will be writing assemblers and linkers in the class, the next few levels down. Okay. Let's move on down. So you have the assembly code. Now you have to go through the assembler. So the assembly input here is the assembly language, and the output is going to be object code, like binary. But this is only for one module in your program, right? So the assembler only sees one piece of your program, the same way the C compiler only sees one .c file at a time. So this .o file that you produce, some information that you need is not there yet to finish building this. So what you have to do is, as well as the actual object code, on the side are some tables that are used by other tools to fill in the missing pieces that you'll only realize once you put all the pieces together to make a single executable, right? So you're compiling this one module by itself, but keeping track of all the information you will need later from other pieces to build the final executable. Now the assembler reads the assembly language, and in the assembly language, as well as the assembly instructions, there are what's called directives, which are sort of instructions to the assembler about what to do with the following code. And the assembler is going to read and use those directives. It's also going to look at those pseudo instructions and expand them out into real machine instructions, produce the actual machine code, and then produce this object file which contains that machine code plus some information about how to link it together with the other pieces later on when you get to the linker stage. So just to dive into some of the assembler directives. So these are just textual commands you add into the assembly file that tell the assembler what to do with stuff. And they usually begin with a dot in MIPS assembly code, and actually most assemblers. So the directive .text says that all the following instructions, or all the following stuff, whatever it is, should live in the text section. So remember when we looked at the MIPS memory map, we laid out these 4 areas of memory, right? There was the text section which held the program code. There was the static data section which held data that was defined, lived for the whole duration of your program and defined outside any function in your C program, right? So that's a different section, the data section. Then there was the heap and the stack. And so the second directive .data says that the following items should be placed in the .data section. So what's going to happen is each one of these .O's is going to tell you what it's going to contribute to the text section and the data section and any other sections. When the linker puts these things together, it's going to aggregate all the different .text pieces into a single .text and all the different .data pieces into a single .data. That's going to happen later. Okay. Some other things, information you keep track of in this object file are what are the global symbols? What are locations in this object file that other pieces of code in different object files may need to know about? So one example is a function. So if I have the printf.o file that contains a printf function, you want to export the label printf so that other routines in other functions and other files can call the printf function, right? So you need to explain to the following linker that there's this function called printf in this file, and here's where it is in this file, right? So this is the connecting information you store in the object file. Another thing you can have as a directive is just initializing data. So stuff that lives in the static data section, you can explicitly initialize it in the assembly file. So one example is if you say .ASCII-Z and then a string, it will store the characters of that string at this point in whichever section you're in and terminate with a 0 character, right? So that's a way of initializing data in the static data section and telling the assembler to do this, right? So when this program is loaded into memory later on, this string data will be present at that location in this section. If you want something to know where this string is, you have to put a label on it beforehand, so that label then be used to symbolically refer to that address that string appears at, right? But this is how you actually insert the data for the string. And similarly, you can put in an array of words or just initialize some of that, the data section with any random words of memory. In fact, you can initialize any piece of any section. So you could do a .word inside a .text section, right? You can actually add data in line into where the program lives if you wanted to, right? So these are just directives to the assembler. So let's talk a little about this pseudo instruction replacement. Let's give a few more examples so you're comfortable with this. So MIPS actually has quite a rich set of these. It's a bit unusual in this. One example is you can do a subtract by an immediate. So subtract 32 from the stack pointer. There's no subtract immediate in the MIPS instruction set. So what this turns into is an add immediate of minus 32. Okay, so the assembler will make this translation for you. You can actually store a 64-bit word by using a store double pseudo instruction. And in the 32-bit MIPS, 2 consecutive registers are used to hold a 64-bit value. So it'll expand it that way. So you just turn it into 2 separate stores at 2 locations separated by 4 bytes. Multiply, I want to talk about next. We haven't really talked about multiply and divide in MIPS. This is integer multiply and integer divide. There's a pseudo instruction in MIPS called mul, just 3 letters, M-U-L. which takes the 3 registers you would expect, 2 sources and a destination, multiplies 2 numbers and places the result in the destination. However, MIPS doesn't actually have a hardware instruction that does multiply that way. It has a lower level instruction called mult. There's a typo here, that should be a T. That multiplies 2 numbers, but the results don't go into registers, they go into 2 special locations, 2 special registers called high and low. I'll talk about those in a minute. And then you have to actually retrieve the result from the low register here, T7. So this mul turns into these 2 instructions in MIPS. So other examples, you can actually say add U with an immediate. I'll actually expand it into the right opcode, right? You can do more complex branch conditions. You can say branch if less than equal 1 register to an immediate, and the assembler will generate a sequence that first loads the right immediate and then branches, does a set less than on it and then branches on it. Now notice in this example, we had branch if less than or equal this register to the value 100. What the assembler was smart enough to do was say, oh, actually, what we're going to do is set if less than T0 than 101. So this is less than or equal 100. That's the same as less than 101. We have a set less than immediate instruction, so it's set if less than immediate than 101. And notice it puts the binary value of whether that was true or not into that assembler temporary register, $AT. Right? And then that's the value you check against 0 in the actual branch. So this turns into these 2 instructions. Another important case is at some point in your code, you want to find the address of some location in memory, say a static data variable. You want to find its address. You can just say LA and the symbol name in the assembly code. Now, I previously talked about how you could do a .struz ASCII Z directive to place some characters in memory, and you could prepend a label to that saying this is, str. Right, this is str, and this is then the data that fills in what str is. That label you can use in this load address. Then what the assembler is going to generate are 2 machine instructions that are that will be filled in later with the actual address of that string. So one's a load upper immediate. Remember, load upper immediate takes 16 bits and puts them at the top 16 bits of a word, and 0 is the bottom 16 bits. So that's the high 16 bits of the address. And then or immediate or is in the bottom 16 bits of the address. Now, one thing is, at this point when the assembler is looking at this single file, it may not know where str is. It may be in a different file, right? And so this is a hole we're going to have to patch up later, and this is one of the functions of the linker, is to resolve all these references between all these individual modules. The assembler has to first make space for that to happen by expanding this into these 2 machine instructions. Let's just dive down into multiply and divide, because so far we haven't told you about this in MIPS. So classic multiplication, you all know from, high school, kindergarten, or preschool. I don't know where people learn this now. How to do integer multiplication, right? Longhand, you do the digits 1 by 1, and then you shift along and add them all up. And this is, not a bad way of doing it in the processor as well. But one thing to notice, when you multiply 2 n-digit number by an m-digit number, you get an n plus m digit result, right? The possible output is much bigger than either of the 2 inputs, right? So m by m bits, you get an m plus n bit product. So on MIPS, if you multiply a 32-bit number by another 32-bit number, how big can the result be? 64 bits, right? So you have a 64-bit result. Where's that going to live? All our registers are only 32 bits wide. So what they did in the MIPS ISA was they defined the instruction multiply to write the result into 2 special registers called high and low. Well, high is the high 32 bits and low is the low 32 bits. And these are completely different registers from register $0 through $31. These are completely separate registers, high and low. They're only written by the multiply and divide instructions. Okay. So the upper half goes in high, lower half in low. And there's special instructions, move from high and move from low. But first you do the multiply. The results are stored there. Then to get the results into a regular register, you have to do a move from to read from high or read from low the appropriate piece into a 32-bit register. Okay. So if you write this A equals B plus C times C in C, in MIPS code, it will look like this. Here's the multiply instruction. Notice there's a T for the actual machine instruction, and it's just MUL for the pseudo instruction. then move from high or retrieve the value. Notice this multiply only has 2 register names or 2 sources. It doesn't specify a destination because that's implicit. It's always writing to high and low. Okay, then you can move the 2 pieces. Often in C code particularly, you only care about the lower half of the product. So in C, it's defined that if you multiply 2 integers, you get an integer result. The fact that it expands, the high bits are just ignored in C, right? So this pseudo instruction mod just expands into a multiply and the move from low. The move from high is just not needed because you don't need that high word as a result. You can't get at it. Okay, so that's integer multiplying MIPS. Division is kind of similar. And when you do divides, you divide one number by another. It's the classic long division, algorithm. You have a quotient, which is the number of integer versions of the divisor that will fit in there, and the remainder, which is the leftover pieces. And so the MIPS divide instruction calculates both of these for you. It gives you the quotient and the remainder in 2 separate registers, high and low. And so again, you start off with a divide, and it starts off with 2 registers, divides one register by the other, puts the remainder in high and the quotient in low. So these implement the C division and modulo operators. This is actually how it turns into machine code. Now, one thing that's very confusing about MIPS is that I don't know why they did this, but the pseudo instruction for divide is also div. And you just have 3 registers, and that's how you tell them apart. So div with 3 registers will write the quotient into the first one, and div with 2 registers will write it to high and low. For multiply, they have mult and mul. So it's just I don't know why they did that. It just doesn't make any sense to me. It's just what they did. Okay, but be wary of this when you're doing multiply and divide. Okay, those little diversions of multiply and divide. We'll do some administrivia now. Okay, so homework 2 is due Sunday. And you have to register your Project 1 team, 2 people, exactly 2 people, by this Friday. You'll lose EPA if you don't register on time. There's a pin post about finding a partner. We'll also put out Project Part 1 on Sunday. Now, homework 3, we're going to give you a homework 3, but it's not going to be graded. And the purpose of homework 3 is to give you some practice problems for the midterm. Right, we didn't want to overload you with too many graded things coming in at the same time. So this is just a set of practice questions for you to work on for the midterm. Just in the news, so actually, a bit of history here at Berkeley. So 3:30 today, just at the start of class, there was a ceremony over in Soda Hall where the IEEE put up a plaque over there commemorating the first RISC processor. So RISC-1 was developed by a group led by Dave Patterson and Carlos Hacan. They produced the first VLSI RISC processor in 1981 over there. And there's the quotation from the plaque. First RISC processor produced 1980, 1982. Students designed and built the first VLSI RISC in 1981. The simplified instructions of RISC-1 reduced the hardware for instruction, decode, and control, which enabled a flat 32-bit address space, a large set of registers, and pipeline execution. A good match to C programs, the Unix operating system. RISC-1 influenced instruction sets widely used today, including those for game consoles, smartphones, and tablets. So the ARM cores in your iPhone and iPad are based on RISC ideas that actually were influenced directly by stuff done here at Berkeley. So here's video history. Okay, let's take a 2-minute break. Okay, let's get going again. All right, so let's start going through. We sort of went through the whole pass from how you get down to an object file. Let's talk about some of the issues that show up, though, producing machine code. All the simple instructions, like arithmetic operations on registers, those are pretty easy. Everything you need to know is kind of within that one instruction. Add 3 to 4 and put it in 5. More complex ones are something like a branch. Now, in a branch, you need to specify a target place to jump to if the branch is taken, right? So if some condition is true, I'm going to jump to some target address. Now, if you think about it, I wrote it as, in my assembly file, I had the branch instruction go into a label. The label's somewhere here with a colon next to it. In between are a whole bunch of instructions. I don't know until I expand those instructions how big they are, because some of them are pseudo-instructions. There may be actually 2 or 3 native instructions. So I don't know how far away the branch is from the label until I've looked at everything in the file. You get this forward reference problem. As I scan the file, I see a branch, but say the branch, here's a branch to label L2, but this label L2, I don't know how far ahead that label L2 is at this point in the text. I have to keep going till I see label 2. I also have to keep track of how many instructions in the meantime and how many of those expanded out to more machine instructions. So usually do this in 2 passes. So the first pass, you'll read through the file, find all the labels. In the second pass, you will go back through and generate the code now that you know where all the labels are. So you know the relative offsets. Remember, the branch encodes the target as an offset from the current PC, or actually PC plus 4, right? So the 16-bit immediate field in a branch is the number of instructions plus or minus where the target is located, right? So often you'll do 2 passes of the assembly code to find all the labels first time, and second time through actually fill in all the offsets for the branch instructions. Now, as for branches, which are usually short distances and almost always within a single assembly file, right? But jumps and jump and link are a bit different. These need an absolute address. Remember, the 26 bits are actually an absolute address that you're going to jump to. And also, they're very often used to link things between object modules. For example, jumping to a subroutine in a different object file. And so you need an absolute address, but you don't actually know where you're going to jump to. Similarly, when you're doing, say, a load address to get the address of a string in the static data section, that string may have been declared in some other module, right? So you know it's in the static data, but you don't know where it is in the static data, right? So when you generate the code here, you produce these. The load address, as I talked about, was broken up into 2 pieces, each of which contributes 16 bits of the final 32-bit address. But I don't know the actual 32-bit address until later, right? So what we have to do in translating this one module is do as much as we can in turning into machine code, and then create tables that say all the things you didn't know that will have to be filled in later by the linker, right? So basically, these are labels for functions. What are all the functions I'm calling? These are the functions you need to fill in for me. Also, all the data I'm referencing, tell me where all this stuff is going to live in the static data, right? And then fill it in. So this is all placed into what's called a relocation table, which is information in that .object file that is used by the linker to find all these pieces and basically patch up everything so it all works together. So every label that's jumped to, and this can be internal or external, because you may actually declare these are functions I'm going to jump to, and I need to know those addresses, as well as these are functions within my module that somebody else may need to know about. So it works 2 ways, right? I can call a function somewhere else. Somebody else can call this function. I need to export both those pieces of information, the things I'm interested in and the things I'm providing to other modules. And also any piece of data in the static data section. So in the object file format, it's a little bit more complicated now. It's not just a string of 1s and 0s holding the machine code. That's one part of the file, but there's several other sections in that file. And this is all standardized. So there's an object file header that tells you, how big all the other segments are in the file. There's the text segment that does hold the machine code as far down as you've managed to refine it thus far. There's the data segment, which holds all the initialized data from this file. And then there's the relocation information that says what lines of code need to get fixed up later. And then there's a symbol table, which basically says all the labels and interesting points in this file for other people to use, right? So the relocation information is things I need to get resolved and patched in this file. The symbol table is addresses that other files will need to know to access stuff inside this file, all right? So this is kind of what you're importing, and this is what you're exporting from this object file. Also, in addition to this, usually you pack in a lot of debugging information that helps, for example, programmers realize this line of C code, where did this machine code come from? At this point, you'll actually put in pointers saying, you know, this file at this line number is the C code that generated this particular machine instruction. So when you have a source level debugger stepping through the machine code, it can keep track of where that came from in your original C file to help programmers debug the level assembly code, all right? So all this information has to be packaged in a standard format, and the dominant format these days is called ELF, executable linker format, and almost everybody uses this except Microsoft to hold program information. So it's a very standard format. Notice the format itself is independent of the ISA. For every given ISA, there's a specific instance of this format, but you can write generic ELF readers right as understand the format for any ISA. Right, so ELF is a dominant standard format these days representing all this information, okay? But remember, this piece, the text segment, is the actual machine code, the actual program. That's all that piece is. The rest is all the information you need to combine this with everything else to make it executable. All right, so we got as far now as generating this 1.0 file, like one foo.c file. It got compiled to one foo.s assembly file, which got compiled down to one foo.o object file. You may have 100 or 1,000 or 10,000 .o files you have to combine to make an executable, right? And that's what the linker does. It takes all those individual files, combines them, and builds a single text section, a single data section, and a single set of other debugging information that's used, that's packed into your executable that you can then run, okay? And one other thing the linker does is bring in standard libraries, right? Typically, most programs, you write very little of the code that finishes up in a program. You write a small piece, you put in a little library code that's pre-compiled and pre-written. That's also pulled in by the linker at the same time. Okay, so the linker, what does this see? Well, the linker's input is all these object code files, and they contain all the, inside the object files is a lot of internal information to help the linker. Also, some of the object files that come from libraries, right? So you link together user's program plus all these library files. And the output's going to be an executable for the machine you're running on, like MIPS. So convention on Unix machines, that's called a.out. I forget where the name comes from, but that's just the name they've been using for forever. You can rename it to anything you want. So one interesting thing to note about this link process is, one good thing about this is it lets you do incremental compilation. If I just change one C file, I just have to recompile, reassemble that one C file into a .o file, and then just redo the link piece. I don't have to recompile everything in the whole world. Just that one component is one of the advantages here. Okay, and this is really important when you work on big systems. So one example here is like Windows NT. You know, something like 40 million lines of code. It's probably more than that now in Windows 10. It's probably, 50, 60 million lines of code. You don't really want to have to recompile all of that every time you figure out you're off by one in some constant in a file somewhere, right? And actually building an operating system these days, it probably takes sort of 8 to 10 hours to rebuild the whole system like this on a modern machine. Okay, so this schematically what the link is doing is taking two object files. This is just showing two of them. So each one has some text, some data, and some information, right? And the linker puts this all together, uses the information to put the text together and put the data together into a single file, right? So then it becomes a single executable. So you're going to take the text from each file, put those together, take the data from each file, put those together, and sort of lay them out in that standard memory map we said, with the text at the bottom and the data next. It's also going to resolve all the references. So for every file, you look to see what external references does it need. You go find where those are in other files using the other table, the symbol table, and then you patch up all the individual instructions in each file that need patching with the actual addresses of where those pieces ended up in the global memory map. So we have to talk about the different kinds of addresses you have. So branches are easy because they're just PC relative addresses. So you don't have to change those. No matter where that piece of code ends up in the final program, it's going to be plus or minus whatever number of instructions for that branch. So those are great. You don't have to touch those after you generate them, right? But functions, you have to figure out, if I jump to the printf code, where is the printf code in absolute addressing in memory? Also, if I have some static data, where does it actually live in the static data section? So all these things have to be patched up. So let's dive down into the instruction formats. This is now the machine code, the actual machine format. So remember, jump instructions had a 6-bit opcode, then a 26-bit address. That was word aligned, so you multiply that by 4, then take the top bits from the PC. But this is basically an absolute address to a function. Loads and stores to the global section on MIPS are done by an offset from this one register GP, which is the global pointer that points to the start of the static data. So the convention is, all the way while your program is running, GP points to the start of the static data, that one register. Then you can just use offsets from it to get to individual variables that are in that static data section, okay? But now you need to patch in, what is the offset? Where is this particular static variable relative to the start of the static data section, right? The start is held in GP. The offset tells you where in that static data section the data is held. Conditional branches are easy, like I said. They're just, they don't move around. But these two things you have to fill in, the offsets to the global pointer and the locations of the functions in the global address space. All right, so how does it do this? Well, it starts off by knowing where the text segment in MIPS starts at location hex 400000, right? That's just where the convention says program memory starts in a MIPS executable. It then takes the first object file, puts its text at the beginning there. Second object file, just stacks them on top of each other, right? So you just fill out the text section with all these individual pieces of programs. Then you can assign an address to every function that appears there, right? Similarly with the static data, you take the static data section from the first file, put that down, and go through. But you need to know how big the text is before you know where the static data starts, right? But you know the offset from the start of there. And you notice that in the for static data, using GP to point at the base. So you don't actually need to know the absolute address. You just need to know relative to the start of the static data, where is each variable located, right? Okay, so the link is sort of putting this all together, building the global picture, assigning absolute addresses to all the labels. Then it goes in and patches the machine code and fills in those offset fields with the right values, right? So, you know, if you see a symbol, it has to search all these tables to figure out where is printf, which module has printf in, and where did I put that module in the global memory map. That gives me an address I can then go and patch into every jump and link that calls printf, right? So the final result of this is an executable file with all the references resolved and all the jumps go to the right place, all the loads of static data load the right offset from the global pointer, then hopefully your program should run, right? That's the job of the linker, to build a single big executable. So when it's done that, you have this a.out. So this is now just a file on disk that contains a complete text region and a complete static data section that now you can load and run. So that's the job of the loader. So the loader used to be a separate program that would take the executable file and run it, right? So the executable is on disk. The loader's job is to get it going. And these days, that's done by the operating system, right? Now, this functionality is still called loader because in the old days, there used to be a loader that did that loading. And that was a program that ran, overrode itself with a program, and then disappeared, right? When you can only have one program running at a time. These days, you have multiple programs running at the same time. So the operating system is doing this functionality for you, all right? Okay, but what does the OS have to do? So what is a loader actually doing? Well, on disk, you have this sort of version of the program, a data file describing the program. The loader has to actually create a running image, which means it has to read the header, figure out how big the pieces are, allocate space, create a new address space that this program is going to run in. We'll talk about virtual memory later. But basically, you create a whole new address space starting from 0 and all the way up that this program is going to run in. You then copy into memory from the disk file the text section, the data section to initialize it. You then initialize the stack by actually pushing on the arguments. Remember we had the argv and argc arguments to main. Those are actually pushed on the stack first and pointed back to those. And so then the main function can find its arguments. Then you initialize the machine registers and jump to the start of main, right? The main, remember, was the one function entry point to your whole program. Somewhere in your C program, you have to have a main, because that's what the loader is going to try and jump to start your program off. So basically, loader initializes everything in the memory image, then jumps to main. And then your program starts running. And then at the end, well, another important thing is how does your program finish? Well, it might crash. Probably the most common thing it does is crash. If you're lucky, it gets to the end, it exits cleanly. At that exit, it'll jump back into the OS functionality to clean up the space, deallocate the memory, and move on. You're ready for the next program. Okay, it's clicker time. So let me explain this just a little bit. So the question here is, at what point in that whole chain do you actually fill in all the bits for one instruction? Do you actually know all the bits for each instruction, right? All the machine code bits. And there's 2 instructions, and so for each of them we're asking the question, and which combination is correct? Okay, I'll give you 2 minutes. Okay. Let's take a look. Okay. So we have a clear favorite, but it's not unanimous yet. So, okay, talk to your neighbors and figure it out next couple minutes. Give you another couple minutes to think about this a bit more. Okay, so I think we have agreement now. Okay. So, yep, that's the right answer. I just want to go through all the other alternatives. So it's definitely not after compilation because when you compile, you just get the assembly code out, and for example, you don't know where printf is going to be. You've just compiled one function. You don't know where printf is going to be. One, after compilation, well, you know that this isn't true because after assembly, you still don't know where this printf is coming from, right? So instruction 2, it has to be after linking. Only then do I actually know the bits I need to put in to jump to the printf function, because it might be in some other file. It probably is, right? So it has to be after linking for number 2. Then the question is it after assembly or after compilation? Well, in some sense, you might know what the bits are after compilation. I know it's an add and it's just registered, so I know the bits are determined. But the compiler doesn't have to care about the actual bits, right? So they actually, the right answer is after assembly when you actually fill in. The assembler takes the IDU, fills in the opcode bits, and does the formatting and everything else. So C was the right answer there. Okay, let's get going. So what I want to do now is just kind of walk you through a real piece of code and look at all these steps with this real piece of code. So here's a complete C program. It includes stdio.h. And actually, what the header file is there for, it should be a bit clearer now why you have these header files. That encodes information that tells the C compiler what to expect will be coming in from other places in the program. So the header file says there will be a printf, it'll be in a different module, but this is what it looks like. And that's what the header file is really doing. It's the way that you link this C compilation with all the other pieces of code in your program without the compiler having to go look at all the other pieces of code in the program. It just has to look at the information in the header file, right? So here's the main function. It takes in the arguments here, declares a couple of integer variables, loops around, calculating the sum of the first 100 squares, then prints out the result, and then exits, okay? So printf, the function, lives somewhere else. It lives in the C library, so it won't be part of this C compilation. So let's take a look at the output of the compiler. So the compiler takes that C code and produces assembly code. And this is high-level assembly code, the sort of pseudo-instruction level of assembly code. So notice the first thing is a .text that says the following stuff is program code that should live in the text section of the final executable, right? .align is another directive to the assembler. What .align says is make sure that when you put this in memory, it's at a memory location that's aligned on some multiple of, and the argument is actually a power of 2, so 2 to the 2 bytes. So aligned on a 2 to the 2 bytes boundary, the following stuff. Why is it 2 to the 2? 4. I'll tell you what 2 to the 2 is. So 2 squared is 4. Why is it on a multiple of 4 bytes? Yep. That's right, yeah. So instructions are a word. So instructions have to be aligned on a 4-byte boundary. So this is telling the assembler, this following stuff you put out better be aligned on a 4-byte boundary. And the next directive, .global main, says main is a symbol, it's a name that should be globally visible. So when you assemble this file, put this name in the symbol table so that other files can find this location, right? So someone else can find out what's the address of main in a different compilation module. Then you have the actual label. This is where main is in this file, main colon. And here's the machine code. So notice we have the instructions here. This is the function prologue. It's setting up the stack. It's allocating space for that main function. So it's decrementing the stack by 32. It's saving 4 registers onto the stack. And notice here, it's storing 0 twice to the stack. What is it saving there? Why 2 locations? Why is it storing 0 to the stack? Here's the original source code. Why is it storing 0 to 2 locations on the stack? Yep. argc and argv. No. Let's try again. It's not that. Right, yes, exactly. So the sum variable and the I variable. Notice these are two local variables inside this function. So local variables inside a function are allocated on the stack. In the code, they're initialized to 0, right? So I and sum are being set to 0. So that's what's happening here. These are locations for I and sum. And so this is saving two registers onto the stack frame. And this is initializing those two registers, local variables, that live in the stack frame as well. So remember, the stack frame has the saved registers plus the local variables of the function, right? Then here's a loop. So the loop starts here with this loop label, and the loop ends here with a branch back at the end of the loop. So it loads this variable from the stack, right? Does the multiply, squares it, and notice this is the pseudo instruction, right? Loads the other variable, adds the multiply result to the sum, and stores it back to the stack, right? Increments this loop counter, or adds one to it, stores that back to the stack, branches back to the top of the loop, right? So this is incrementing the I. He'll reload I again, do the multiply, square it, check it again, right? Then when the loop is done, you're now setting up, so this routine is going to call another routine. It's going to call printf, right? So what you're going to remember up here, you actually save the return address here because this is not a leaf. Main is calling a different function, so main is not a leaf function. It's calling printf, so you set up the argument in A0 and A1. So the argument, the printf format string, this string here, like in your C code, is actually just here in the assembly code. So notice what's happened. At the bottom here, I've changed the .data, telling the assembler put the following stuff inside the data section now. Right, this is static data. And align it 0, I don't care how you align this, because this is just a byte string, so bytes can start anywhere. And then at this label str, place this 0 terminated string, which is exactly the format string the programmer wrote in their C program. Right, so just creating in the static data section, initializing an array of bytes with that string. So to pass that as an argument to printf, you do load address of str into A0, and we'll see this get expanded later. So A0 will then have a pointer to this string, right? And then you also load the value you're going to print, the result, which is stored on the stack. Then you jump and link to printf. You now call the printf routine to do all the work of printf. Then when you come back, printf produces a result, which you ignore. You clear this variable, which is the return value. So V0 is the return from main. Because the code executed correctly, you just put 0 in the return value from main. Then it restores the return address, deallocates the stack, and then jumps back from main. This will then jump into the sort of runtime system that started your program, which initially called main. You jump back to it, and it'll see there's an exit code of 0, and everything will be fine. Right? So that's what's in the assembly code that comes out of that C program. Right? So this is enough information now for the assembler to generate the object file for this little C program. Okay? Okay, there's a bunch of pseudo instructions in here. Where are they? Where are the 7 pseudo instructions? What's the first one? Sub U, right? Where's the next one? Mul. No, that's one as well. The others? We've got mul already. Move. Load address. And this one, branch of less than equal, right? So these are the, okay, you missed one. So those are the pseudo instructions. So this is just shorthand. You know, the compiler or a human typing assembly code could just quickly output these, and the assembler would just do a little bit of work to expand these into the real instructions, okay? Okay, so now we have the assembly file. Now we feed that into the assembler, which is going to generate the machine code file, okay? So, and these are the addresses it's given. So notice that this is a, you know, valid 4-byte boundary, 00. And so that pseudo instruction has been expanded into a, instead of subtract 32 from the stack pointer, is add immediate unsigned minus 32, right? These are the stores on the stack. Let's go through. Multiply has been expanded. Here's the multiplies, the move from low. That was the add, turn into an add immediate. This was the loop that was less than 100. Less than or equal to 100 is actually less than 101. And now this was the load address. Remember, you had to get the pointer to the string. So that turned into two instructions that gives the high 16-bit and the low 16-bit of the address. And now what the assembler has done is left some, in a separate table, record the fact that you need to patch this low part of the string address, the left part of the string address, and the right part of the string address, the high piece and the low piece, have to be patched into these locations. Okay. Now notice that the string lives in a data section, and you don't know where that data section is going to end up in absolute addressing until you've compiled the whole program, right? Because the linker is going to take all the data sections and concatenate them into one data section that's going to sit on top of the global pointer, which sits on top of the text section. So this information you don't actually know at this point, like what these bits should be in these instructions, right? The same with the printf. You don't actually know where the printf function is going to be in the final program. So you just have kind of a hole there waiting to be filled in the machine code object file that you've generated, right? So the assembler also creates, along with those machine code instructions with some holes in, a table that says how to fill the holes in. So there's a symbol table that says the things defined in this object file, where are they inside this object file so others can link to them, right? And so this is relative to where they are in this section inside this file, and also what type they are. So the main is a global program entry point. Loop is a local text entry point. So this label loop is only visible inside this 1.0 file. You don't export that label elsewhere. You don't need anybody else to know about that loop label, right? And you can imagine in a big program, you're going to have thousands of different loop labels, right? You don't have them clashing in names. The purpose of this global main here was to say that main is actually a name you want to export out that any other module can see, right? So if it's not explicitly made global, it's assumed to be local to one file and nothing else needs to see it, right? So if you try in another file, say you tried to jump and link to loop, it would just fail because loop was not visible externally. Nobody knows where loop is, right? It's only the symbols you export and declare as being global that are visible and you can link to from other files, right? So global main here is the little trick in the assembly file to tell the linker, to tell the assembler to generate the symbol table information saying this is global and hence should be visible from other parts of the program. So str was a string, and again, this was local data. So that string, the format string inside the printf, you don't want to have that visible to any other random piece of the code. It's really private to that module. And so you don't make that global, and hence it's only visible locally within this module. So that's what this type tells you. Now the relocation information, so the symbol table says what this module is exporting to the outside world, all the symbols inside this module. The relocation information says what information does it need to receive in order to finish patching itself up, right? So what it needs to do is find where the string ends up in the global space, right? So this is a top half, high bits of the address, the low bits of the address. Somebody's head's in the way. And then down here, you also need to find the address of the printf to fill in a jump and link, right? So this is the relocation information needed for this .o file. Okay, so, well, I guess one step you can do is anything that's PC relative you can patch up. So this branch here to loop, that's just local, so you can just do that within the single file, just minus 10 instructions. All right, so finally the assembler spits out this information in a .o file, right? Puts everything out there. Has the instructions, the data segment, and symbol and relocation tables. And it has sort of placeholders for everything it couldn't figure out that need to get patched later. So, schematically, if you look at that object file, it looks something like this. Here's the bits. These green fields are the things that need to get filled in, right? So this is the high and low 16 bits of the string offset in the global data space, and these 26 bits are where the printf function will live in the global address space, right? So you generate the code with kind of these holes in. The linker is going to use all the metadata to patch these holes later, all right? So one thing you'll see if you start using disassemblers to look at machine code, a disassembler takes the object file and tells you what's in there in human readable assembly code. If you do it on a .o file, you'll see that some of the labels are just not there because the information, it doesn't know where it's supposed to link to, right? But if you do a disassembly on the entire program, everything should have been resolved and you actually see where everything jumps to, right? And this is the reason why the information is just not there in the .o file. Okay, so linking, first step is you got to combine all those .o files. Right now I have these many different .o files. Yep, question? So dotted line, so remember what's happening here is the assembler is reading this text and sort of filling in sort of memory images like arrays of bits and arrays of bytes. The dotted line is just a directive telling the assembler that the next thing you do should be aligned on a certain boundary. So align 2 means align on a 2 to the 2 boundary or a 4-byte boundary. And what it'll do, insert zeros until the address it's at is a multiple of 4. And that means it's a valid address, in this case, for an instruction. Now, the data section had a dotted line 0, so 2 to the 0 is 1. That meant a line on any byte boundary, any multiple of 1, is fine because it's just a byte string. I don't care where it starts. Any address is fine. So the argument is a power of 2. So you could be a line, dotted line 4 would say put on a 16-byte boundary. Dotted line 5, a 32-byte boundary. And so and all it does is pad with zeros until it gets to the next multiple of that alignment value. Okay, so now linker has all these separate .os. It's trying to put all the pieces together to make the whole program. So first thing it does is take all the text sections, sort of line them all up and build a big text section. Take all the data sections, line them all up and build a big data section. At that point, it knows the relative location, or the absolute location of all the text, the relative location of all the data. It can then look across all the symbol tables and fill them all in so everybody knows where everybody is, everything is. And then it can start looking module by module and seeing what needs to be patched. And look in the global symbol table, figure out where all the addresses are, and actually fix up all those missing fields in each of those modules, right? So the relocation information would say something like, in this .o file at this location is this kind of instruction that has this kind of data needs to get filled in. So you just kind of run through. Once you've gathered all the information, you can go through and patch everything up. And so now, for example, it would just insert these immediate fields into those instructions with the correct final addresses, right? So all that stuff gets patched up. So then the final thing the linker does is just spit out as a final executable file the result of this merge. So all the bits are merged together. You have a single executable. So there's one text segment, there's one data segment, and there's a header file saying how big everything is, right? The standard ELF executable format. This was a simplified version of ELF. If you go look at the ELF spec, there's many, many other bits of information and different kinds of segment happening, but this is enough to kind of get the idea of what's going on. So one thing to say, what we talked about here is what's called statically linked libraries. So here we took all the libraries your program needs, all the code you wrote, and in one go build a single executable ahead of time that contains all the library code and everything. And you just run this on your system. All the information is inside the executable file. Now, one of the issues with this is that, say that there's a bug fix in one of the libraries. So say there's a, security bug is found in one of the libraries, right? That's a pretty common example these days. Now, what you could do is go back and relink all your code against that fixed new static library. And that's what you'd have to do if everything's statically linked. But these days, another problem is that if you imagine on a laptop where you're running, say, 100 different processes are running, 100 different programs are running, and they all link with the same libraries, you'll have 100 different copies of the same library in memory at the same time. And that's kind of wasteful, right? And so a very common technique in modern operating systems is what's called dynamic linking. And the idea there is you link all the non-common pieces of your program, all the things the user wrote for the application, into a program, but you don't include all the standard libraries. You just leave stubs saying, I need to call, say, printf at this point in the code, but it's not actually linked in with the code, just the stub saying, I need to call printf. When the program's running, when it hits that call and says, I actually need to call printf, the little stub does the right thing, and only at that point goes, finds printf in the library and links it in dynamically. And what's more, there can be a single copy of printf in your whole machine's memory that everybody points to. So all the programs are sharing one instance of the library and memory. And so that's a very common technique these days called dynamic linking. It's very common on even Windows, Unix platforms, on the Macs. It is actually pretty complicated, and you need to know a lot more about operating systems to actually figure out how that works. But that is something you'll hear about, so I just wanted to mention it at this point. Yeah, I think I said all these things. Another important thing is upgrade. So if you can change the library, you don't need to rebuild your program. It'll just automatically grab the new DLL. One of the issues there is sometimes the new library fixes one bug but causes another, right? And maybe your program was fine with the old DLL but doesn't actually work with the new DLL, and that's a major problem with DLLs. And sometimes you just have to start from scratch. It's pretty bad. But usually the benefits outweigh the drawbacks. There's a lot of complexity, but these days most things use dynamic linking, most systems. Okay, let's just stop that. Okay, so in conclusion, just to summarize what we did today. So compiler takes a high level. We did all this, and we even short on time. Look at that, early. Compiler converts high-level code into a semi-language file, removes pseudo instructions, generates assembly, generates single .o files. The linker pulls all those together, resolves all the cross-module references, and includes the library files, produces an executable that we can load and run. Okay, memory being the execution. Okay, that's it. See you next week.